record. And we will start it. Good, at 10:37. Nice. Okay, so let me do one more step. I think we'll be ready to go here. Screen share so you can see my doodle pad. Around, excellent. Okay, all right, let's read the question here together. You said number 8, let me scroll down. A toroid has a major radius, capital R, and a minor radius of lowercase r, and it's tightly wound around, end turns of wire as shown in the figure. So figure probably down here a little bit. Yeah, there it is. Okay, so I'll try to draw something close to that. I'll do kind of maybe a cross section here at first, and then maybe try to give a three-dimensional arc to it. So this would be the back half, and then as the picture shows, we're going to do a cutaway from the front half. So we don't really see the front half of it. But going to the outer radius is capital R, and going to the inner radius is lowercase r. And what's going to come out to be real important here is this A for area. And then they got these loops of wire wrapped around. Let me not try to figure out which way the current is going, if at all. Yet, because I haven't read all the question, but there's the picture. It says, now, if capital R is much bigger than little r, the magnetic field in the region enclosed by the wire of a toroid, the cross-sectional area. Oh, my bad. I read it wrong. Okay. I did not label this right. A toroid has a major axis of capital R. Now, I read that as inner and outer radius. And so my apology here, looking closer at the picture, a major axis would be just to the center line. Okay. Toroid has a major radius, capital R, and a minor radius. And so the minor radius is just the size of this opening. Okay. And that makes a big difference, a huge difference between what I was reading, inner radius and outer. So again, my apologies. So the main radius or the major radius is capital R, and then the radius of the tube part is little r. See, and I think that's real important here. When they make this statement, capital R is much bigger than little r. And if I do talk about then an outer radius and an inner radius, the outer radius would then be R plus little, or capital R plus little r. And the inner radius would be capital R minus little r. And what I think they're getting at is in both cases, then, since capital R is much bigger than little r, we can roughly say that the radius here of where the magnetic field is, that is the tube part of it, is just capital R. And that's, I think, what they're going to say here. If capital R is much, much greater than little r, the magnetic field in the region enclosed by the circuits of the toroid has a cross-sectional area. So this area is pi r squared, is essentially the same magnetic field as a solenoid. So in other words, the magnetic field of a toroid, and so we need to go back to our toroid, which I guess would be chapter 30, and say that if you take the number of turns times mu naught times the current over 2 pi r, that is the magnetic field in the toroid. Now, for this r, I don't mean the little r here, but r as measured from the center. So they're trying to kind of make things a little simpler for us by saying this, that you can roughly say that the magnetic field everywhere inside of this toroid and the tunnel part of the toroid is given by this equation. The truth is, if you look more accurately at the equation, the magnetic field at the outer radius is a little smaller than the magnetic field at the inner radius. And so there is a variation in the field, stronger on the inside and weaker on the outside. But if this is true right here, where there's very little variation from inner to outer radius, we could then roughly kind of average it and say, why don't we just calculate the field at the center? So that would be at the major axis, and just say that's pretty much the field everywhere. It's true that this number right here, this average, would be a little low for parts that are near the inner radius, but it would be a little high for parts that are outside the radius. So I think that's what they're after in this one. So this has an approximational calculation, not a perfect exact calculation. Oh, I better put page 1 up here on the top, because I have a feeling this might go pretty long here, because I see there's a lot more to the question. I haven't even read it here. All right, but that's why the author says is essentially the same as the magnetic field as a solenoid. In other words, a solenoid just has a constant magnetic field. All right. So essentially the same as the magnetic field from a solenoid that has been bent into a large circle of radius capital A. Modeling the field as a uniform field. Okay, there it is. My hunch was correct in the sense that they just want us to model this as a uniform field, kind of the average at the major axis. So as a uniform field of a long solenoid, show that the induction of such a toroid is approximately given by this. And then it says an exact expression of the inductance of a toroid for a rectangular cross section. So it's easier to calculate for a rectangular cross section, is the whole point of problem number 57. So we'll do a more exact one later on in problem 57. I think that's part of your homework. But right now, we're just do an approximation. And actually, let me do this 2 ways, because I think what the author wants you to do, because he gave that hint that it's essentially a solenoid, the easy way. So I'll do the easy way first, and then I'll go to the more exact, or no, I shouldn't say more exact, the more fundamental. We're still going to use this approximation. So we're not going to do anything exact, but there was a example done, and I'm going to have to grab the book to look it up. And that's why I'm not real fond of my first solution, because it's just kind of a plug and chug from what the book already did. Oops. Yeah, I was about to try to do it from memory, but I'm going to get it wrong here. Let me just grab the textbook, put it in the screen here. It's example number 1, actually. And so right here, in this example number 1, the induction of a solenoid, the author works through and says, this is it. It's mu naught n squared times the area, and of course, this is a solenoid, over the length of the solenoid. So if we kind of use that as our starting point, there was a mu naught, an n squared, an a over the length of the solenoid. Of course, notice I'm going to put that with a lowercase l, not to be confused with the induction, a capital L. if we follow kind of the hint the author's given that you can just think of this as a solenoid, then the length of the solenoid right here would just be 2 pi capital R. And we're done. I mean, that's it. I suppose we could do another step, but they say make it look like this. So we could stop right there, but we could also say the cross-sectional area is this over here. Whoops, I did it to myself again. Bump the keyboard on my laptop and got rid of my screen sharing. Let me just double check. Okay, so I'm still sharing. I just don't see it on my laptop. I'm gonna move my laptop a little further back. Okay, don't keep bumping. Well, I don't have enough room. Gonna bump it. I'll try to be more careful. So I want to scoot it up. That's when I bump it. But I can see that. So, anyways, in desktop, I'm still sharing, so that's good, and I'm still recording. All right. So you could put, when I was about to say the area from this pi little r squared and 2 pi r, and get the pi's to cancel. But that's going a little further than they asked us. They just asked for us to prove this. All right. Now, I'm going to go ahead and do a more fundamental approach and say, well, what if we didn't look up the solenoid from example number 1? What if we just started from fundamentals? All right. So let's look at from the fundamentals. We know this, that here is the definition of inductions, that the induced EMF is equal to minus this L, this inductance, times how the current changes with time. And that came from Faraday's law. Faraday's law, going back a chapter to 31, so what I'd call the fundamental physics is that there is an induced EMF due to a change in magnetic flux. So maybe I should put a little B here for magnetic flux. It's been a while since we've talked about electrical flux, so I don't think anybody would confuse this with electrical flux and Gauss's law, but I should put that there because in the next chapters, we're going to be having both at the same time, and so it's going to be very important we start talking about and labeling, is this electrical flux or is this magnetic flux? So far it's all been, or recently it's all been magnetic flux. We haven't done electrical flux for a good month or more. But like I said, soon to change. Here's what I'm after. So this is the fundamental physics. And this, you might say, is the engineering for applying Faraday's law to a circuit. And so if you apply Faraday's law to a circuit, and I should say a circuit upon itself, which is why we call this self-induction, and connect these two together, you can see both of them have a time derivative. So if you integrate it, both sides, you would get the self-inductance times the current equaling number of turns times the magnetic flux. Not the change anymore, because I'm integrating both sides. Maybe I should even put an integral symbol. Maybe I should also say that I'm canceling off a negative on each side also. But what this leads to, and you'll see this quite a few times on the homework, but also in this example number 1 that I was talking about in the book, the author kind of starts right there and says, look, here's the inductance. And of course, back to page 1, this is what the author came up with. But the author started right here. So I'm going to do that same thing. And I'm just going to put N over I alone for a moment, because the magnetic field is this integral of B dot dA. And so let's come back to page 1 in the picture. The flux, or maybe a different color. I like to do magnetic flux for some reason in green. So let me go with green here. But the magnetic flux, or the magnetic field, as we learned in the previous chapter, or actually further back, chapter 30, was that we would get a field that's inside the tunnel part, and it wraps around, and it follows this equation that we talked about earlier. Okay, so if we then take this problem and say, well, we can approximate the field as being a constant value, then let me use this constant value over here on page 2. And so this would become my N, my I. When I do this dot product, B dA cosine of theta, I can make 2 very useful steps here. The first one is I could say that the magnetic field is, roughly this number and is a constant. So I'll pull that out in front and go N mu I over 2 pi R. So here's the integral. Then I will put the cosine, and we got to come back to the picture to see this, but the angle would be 0 degrees, because if you kind of look at a cross section somewhere in here, maybe right here, the area vector would be, trying to do this in 3 dimensions, would be pointing back into the page, but then so would the field. Or if I did maybe a cross section here, then here the area vector would be pointing to the left, but then so would the field. So whatever cross section you want to pick to calculate the flux, the field and the area are in the same direction, and so that's why there's no angle between them. It's 0. And cosine of 0 is just 1. And then you just have this integral of the area, which is just the area. So the numerator here becomes this n squared, this mu naught, and the I on top and bottom cancel off, and you get your area. And down at the bottom, you get your 2 pi R. And that's exactly what we're supposed to get and prove. So that would be a little bit more from the fundamentals here. Yeah. Anyways, so that would be that one. Your first one, number 8. That's helpful. Okay. Let me jump back over here to your chat and say, all right, what's the other one you put up here? Number 11. Okay. Number 11, let me put the time here. And let's try that one. So let me see something here. Over. Okay, so there's my screen share. Mm-hmm. Okay, not that one. Understand why it does that. However, at least I got it back on my screen for the time being. Okay, I can keep a better eye on. All right, so let's start number 11. And I'll do that by first reading number 11. All right, so number 11, and it looks like it might go on to the next page. Oh, no, it's kind of into just the bottom here. Okay, so number 11 says we have a 12-volt battery, and it is connected into a series circuit containing a 10-ohm resistor and a 2 Henry inductor. What is the time interval for which the current will reach? And then we have 50% and we have 90% of its final value. All right, so let me draw a little circuit here. Maybe I'll start with a battery. So I'm going to put here, so let's call this 12 volts. And it says it's connected in series with a resistor and an inductor. So it doesn't matter what order, since they are in series, probably worth mentioning that. But I'll do the resistor first, since the problem mentioned the resistor first. And so here is a 10 ohm resistor. And then it goes through, and so this is our new piece of circuits here for this chapter, an inductor, and a big inductor. Usually inductors this big are called chokes, as a side note. So here is a choke. The inductance is so big, it really forces the current to be relatively constant. It chokes it, if it will. Doesn't go bigger, doesn't go smaller. I guess I didn't put a switch in here, and that hopefully is implied here because it says what time interval, because what ends up happening here for something like this is our basic first circuit with an inductor, is that if you plot the current versus time and close the switch at time equals to 0, of course, in the negative times, there would be no current. And then it would ramp up. And the reason it doesn't just all of a sudden become 12 volts divided by 10 ohms, like Ohm's law, is because you do get a back EMF from this. But of course, you only get a back EMF during a change. In other words, the voltage is minus L di dt. So the current in the process of changing makes an EMF, and it would be a back EMF. I'll put a plus and a minus there, opposing the current. But the bottom line is eventually things are going to settle all the way down, and there's not going to be any more change of current. And so the back EMF becomes 0. And so we like to say an inductor after a long period of time is just like a wire. There is no voltage on it. In fact, it's exactly the opposite of a capacitor. A capacitor at first has no charge on it, so it has no voltage, and so it's like a wire, no voltage. An inductor is the opposite. After a long period of time, there is no change in current, so there is no voltage, and it's just like a wire. And so I would say after a long period of time, the current settles down to just a simply 12 volts divided by 10 ohms, which is 1.2 amps. So that's why this approaches and eventually settles out at a current of 1.2 amps. And that's important there because when the problem asks for A, 50%, well, we need to know what that number is. 50% of what? So it's 50% of 1.2 amps. So it's, half of that number. So I guess that would be 0.6 amps. Okay. So looking at, and unless you want me to go all the way back and redo the lecture, I probably best if I don't. But like I said, I will if you ask. But this was worked out for the current. It then approaches its maximum. So it was I max times 1 minus e to the minus t tau. In fact, now that I think about it, I still got the book close by. And I still got it opened here to chapter 32. And its very first beginning part is where I, opened it, and they said, here is the idea of the inductance. And like I said, here is where we looked in the last problem where they did example number 1, and they came up with this little formula for the inductance of a solenoid. But in section 2, they actually then put a resistor and inductor in the circuits, and they just then did the Kirchhoff's loop rule here and solved this equation for the currents. And coming out on the next page, here they have it. They got the EMF over the resistance. That's the maximum current. I probably should have wrote it the way they did. And then 1 minus e to the minus t over tau. And it's kind of nice to write it that way because it looks kind of like the same pattern we had for capacitors. Now, the tau is the time constant, and it is the inductance over the resistance, which is important to keep in mind because the tau for the capacitor was resistance times the capacitance. So here we have the resistance on the bottom instead of up in the top like we did for the capacitors. And you can follow that back around, that it, all comes back to the difference between this equation and the equation we did back in chapter 26 when we had capacitors. But, 26 is where we were introduced to capacitors. So it'll be 28 where we put capacitors and resistors together. In either case, this is what I'm trying to show you. So without re-deriving that, I'm going to start there and say, all right, here's my equation, and maybe with this tau equaling L over R. Okay. And so now I can put these numbers in. Let's see, we want the current to be 50%, so that's 0.6. We know it builds up to a maximum. This is that V over R of 1.2. And then we've got 1 minus E to the minus T over tau. And maybe I'll just do tau by itself off here to the side. Okay. So this would be the inductance. Okay, so coming back up to here, this is the 2 Henrys over the 10 ohms. 2 divided by 10 is 0.2. Now, maybe I should, say that very clearly the units must come out to be in seconds, because we have to have no units up here in the exponent to actually calculate it. But that doesn't do it justice. So let me put in the units for Henry. The units for a Henry were really back here when you rearrange this equation and wrote it as the magnitude of the inductance is the EMF divided by the rate at which the current is changing. So we said an inductance of 1, and we'll call it 1 Henry, is when you get 1 volt because the current is changing at 1 amp per second. So a Henry really is 1 volt per amp per second. And so maybe that is better written as a volt over an amp per second with the ohm downstairs. And then you can see that a volt over an ohm is an amp. And so that right there is an amp. It's going to cancel with that amp. So we're going to get 0.2. And that amp cancels with that amp. And then this would be 1 over a second, which is a compound fraction, which becomes 0.2 seconds. So it's nice to see that the units of the Henry over the ohm come out to be a second. But hopefully it's also pretty obvious that it must. And so either way, it's nice for me to show it to you, but after you gain experience, it's probably just like, oh yeah, I know that's going to come out to be second. I can just put that in here. All right. So now I can solve for time because that's the only thing lacking. Maybe I'll bring this 1.2 to the other side. So 0.6 divided by 1.2 is 0.5. And then I get 1 minus e to the t over a 0.2. Maybe now I'll do something like this. I'll remove the parentheses and move this exponential, e to the minus t over 0.2. Move that over there. And then I'll go 1 minus 0.5, which is 0.5. Now it's probably a good time to do a natural log, because a natural log, oops, out of the screen there, sorry. The whole idea of a natural log is to bring the exponent out in front, and then the natural log of e is just 1. So that becomes just a negative t over 0.2. And then on this side, we have natural log of 0.5. So ultimately, we get an equation for time being, and I'll bring the negative to the other side. I'll also bring the 0.2 to the other side. It'll go on top. And I should have mentioned that the negative to the other side would go on the bottom, but a negative on the bottom is the same as a negative on the top. So I'll just bring it to the top. The 0.2 I bring up to the top, and then the natural log of 0.5. And natural log of anything less than 1 is a negative. So the two negatives here are going to make a positive amount of time. That's good. I would be very concerned if I got a negative for time out of all of this. And so maybe I'll just start with the natural log of 0.5. And there it is, a negative number. And then multiply that by a negative 0.2. And so we're looking at 0.139 seconds to build up to half the current. So coming back to my graph, this being half my current, this must be 0.319 seconds. Okay, so there's half of it. Now 90% would be out here somewhere. And you can kind of see by this function that the growth in current isn't as quickly on the second half as it was on the first half. So this might take quite a while to get to 90%, even more than double. Kind of a naive answer would say, well, if it took this long to go to half, then double it and you get the whole thing. Well, it's not a linear growth rate. So that wouldn't be an appropriate logic. So let's try the other part of this, which I guess is part B, which part B, let me read the number again, 90% of its value. All right, so, whoops, let me put B here and page 2 here. Okay, so let me do 90%. So I'm going to go 0.9 of the maximum must equal the maximum times 1 minus e to the minus t over tau, which we've decided is already a 0.2. And then maybe putting all those numbers together. So 0.9, So that's 0.9. And then that would be 1 minus e to the minus t over 0.2. Move this to the other side, e to the minus t over 0.2. Move the 0.9, and so I got 1 minus 0.9, which is 0.1. Take the natural log of both sides. So there's the natural log of 0.1. That would get rid of the exponent and bring that down. Bring the negative over, bring the 0.2 over, and we are left with what time is. So I'll go natural log 0.1. And again, that's a negative number. And that's good because I'm going to multiply by a negative 0.2. Two negatives make a positive. And we're looking at 0.461 seconds. And that does agree with kind of my comment earlier that I think it's going to be more than double this, even though we're not, even though this was the time only to get to half of it, you don't double that to get to the whole current. It's going to take even longer than doubling it to get to 90% because the growth rate has tapered off. So this 90% is way out here at almost a half a second, just shy of a half a second. All right, and let me swing over to the answers just to make sure I didn't do anything crazily wrong. This one seems straightforward enough. Yeah, that matches good, and that matches. All right, nice. Good. Okay. Keep those handy in case you need to come back to those. All right, let me switch back over to the chat. See, the next one you threw at me was, 24. All right, so put a timestamp here. This is, how can it be already 11:15? Oh, yeah, I had that special meeting that started a little slow today, but don't worry, we'll do all these today. Guaranteed, no matter how long it takes. All right, so number 24. All right, let me read number 24. So 24 says the magnetic field inside a superconducting solenoid is 4.5 Teslas. Pretty strong field, really strong field. Not a record-breaking strong field, but very strong. Yeah, Tesla's pretty strong, 4.5 Teslas. So I see why they have a superconducting solenoid. The solenoid has an inner diameter of 6.2 centimeters and a length of 26 centimeters. Determine the magnetic energy density in this field and the energy stored in the magnetic field. All right, so maybe I'll start with a picture of a solenoid. This will be the kind of the core of the solenoid right here. And of course, a solenoid is a current, and I'll just put it in front and behind the back, looping around, coming in front, behind the back, underneath, loop it in front, and then around back. Maybe I better not draw too many because I think this will just get in the way of my picture. Okay. And I'll just label the current in a particular direction for right now, which in my picture then, and going back to chapter 30, using my thumbs up with my fingers representing the currents. And so this is what I call the second right-hand rule. I guess I would grab this solenoid with my fingers curling in the same direction as the current. Current goes up, current goes up, current goes up, current goes up. And it all goes up on the front side and goes down on the back side. So my right hand would be held like this. And so my thumb would be the direction of the magnetic field. So the magnetic field would be in the solenoid and pointing from the right to the left. Okay. Maybe I'll draw it in green as arrows that look like that. All right, so there's my magnetic field and my magnetic flux. And so this question is getting to the energy density. The energy density, we like to use the little symbol mu, and we like to use the B for the energy density in a magnetic field. Because we didn't do much with it, but maybe this would be a good time to point out the analogy to the electric field. When we had a capacitor, we said that the energy would be stored in the capacitor and there'd be an energy density. And we came up with 1/2 epsilon naught electric field squared. So the permittivity of free space and the electric field. So depending on the strength of the field, that represented how much the energy was stored in that field. And we have the same thing here. It is a little different. We still have the 1/2, although, well, and we still have the field squared, but because of the different properties of permeability versus permittivity, it's in the denominator here. But that's what this is getting at. And I should double check that because there's another and a second way of writing that one, but I'm pretty sure this is how your author and I presented it. Here it is, section 3, the magnetic field density. Here we go. And so, yeah, looking on whatever page this is, it's like 904. But there's what I just wrote. The field squared over the 1/2, and then there we go. The permeability is in the denominator instead of the numerator. All right, so again, I'm going to use that equation and just kind of cross the electric field out, but it's, again, good to, I think, to see it for your overall education, partly as a reminder, because coming up in the next chapter, like I said earlier in another problem, is we need to make sure we keep labeling which field we're talking about, because most recently we've been dealing with magnetic field, and earlier on we were dealing with electric field. But as we wrap up this semester, we get into electromagnetics, where the two are going on at the same time. And I need to be careful. Am I talking about the energy of the magnetic field or the energy of the electric field? And that's where we're really in right now, is electromagnetics, because when the magnetic field changes, it makes a back EMF. Well, there it is. That back EMF is an electric field. We had some problems like that in 31. So chapter 31 started our process of electromagnetics, dealing with electric fields and magnetic fields at the same time. All right, well, let me then just do a raw just plug and chug here, because they say the magnetic energy density, and that has just with the field. And just to remind myself and to remind you from chapter 30, the field in a solenoid is the same all the way through. So no matter where you pick inside of the solenoid, you're going to get a field strength of 4.5 Tesla squared. And then the permeability of free space is that 4 pi times 10 to the negative 7. So if we put in some numbers here, we will get 4.5 squared. Guess I'll divide that by a 2. So we'll also divide it by a 4. So we'll also divide it by a pi. And I will also divide it by a 1 times 10 to the negative 7, which is going to make this a big number, 8.06 times 10 to the 1, 2, 3, 4, 5, 6. And this is an energy density, so it would be joules per cubic meter. And there would be A. And in fact, before I go on to B, maybe I'll switch over here to the solution real quick, just to make sure I did the energy density. 8 times 10 to the 6 joules per cubic meter. Nice. So we agree there. Okay. And then B says, well, what is the energy then stored in this magnetic field? Okay, well, you might say this, that energy density would be, and so I'll just go energy density, what we just calculated, would be the total energy, I'll call it E, over the total volume. And maybe I better spell out volume, because I almost put a capital V for volume, which is the normal symbol for it, but we also are using capital V for voltage a lot in this section. So that could be confusing. So this, I'm gonna spell out volume, and then just rearrange this equation. So the total energy would be the energy density times the volume. And so this is the 8.06 times 10 to the 6 joules per cubic meter. And then the volume, and I drew the volume here as a cylinder shape and laying horizontally. It wouldn't really matter whether the solenoid was vertical or horizontal or some combination, the volume would be the same. So I don't have to worry about, is my drawing correct? Although the cross section may not be a solenoid, but I think they imply that when they say the solenoid has an inter diameter of 6.2 centimeters. So they are telling me this diameter. So they're saying it has a circular cross section. And so then it has a length. All right. So when I go for the volume, I need the volume of a cylinder. And I need the radius. Be a little careful. They gave me diameter. So they said 6.2 centimeters is the diameter. So let me cut that in half, and I get 3.1. But also, let me put it in meters so that my cubic meter will end up canceling this volume in cubic. So the 3.1, I'm going to move the decimal to. And I think they also gave me the length somewhere. Yeah, it said it was 26 centimeters long. And again, same logic. Let me change the centimeters into meters so that what I'll get is a square and then a cubic meter, which would cancel with a cubic meter here. And it's going to be left with the total energy stored. It makes sense. Density times volume is going to give you the energy stored. So I still have that number energy density in my calculator from part A. Let me just then go times a pi times a 0.031 squared, and then times a 0.26. And I got 6,324 joules. And that's a lot of energy. I told you the field was strong. These are actually really dangerous to work with. That energy, if not done correctly or something goes wrong, gets released. It's a huge amount of energy released. It's a small explosion. So, in fact, a good example of this is if you ever seen pictures of solar flares. There's this huge magnetic field spiraling out from the sun, and then the field collapses and converts all that energy to kinetic energy, and the parts of the sun go shooting out. And so these solar flares become plasma bursts and they go flying out into space. And they're kind of directed. And luckily, it's highly unlikely that they will get shot over towards the Earth, but they can get shot towards the Earth or near the Earth. And unfortunately, the Earth has a little bit of protection. We have our own magnetic field that protects us. So unlike Mars, where Mars no longer has a magnetic field, and because of that, its atmosphere has been ripped apart, and so it no longer has an atmosphere anymore, too. So it doesn't have its protecting shield. Although, to be quite honest, a direct blast, our Earth wouldn't survive. Our protecting shield is pretty good, but not that strong to handle a direct blast. All right, let's check the answer to that one. Okay, so yeah. Okay, so that answer looks good. All right, let me jump over back to the chat here and go, all right, let's win the next one. 28, and the time is, time's about ready for our first break. That'll be good. I know we started a little bit late, but if you'll be okay with you, I've been talking like crazy. I was starting a little late because I was in a bunch of other discussions and office hours. So I could use a restroom and a drink of water here. So okay with you, let's take our break. And I'm going to actually write these down because we'll lose them, but you can send them back up. Let's see, we did 24. So the next on your list is 28, 37, 40, 45, and 63. Good. So let's start working through those at 12:30. Sound plan? Yeah, good. We will see you in 1 hour.